Okay, so this is my test of my inductor kit. What I've got is I've got a MOSFET on there. Unfortunately, it hasn't got brilliant thermal conduction path, so I have to keep the current down. A couple of caps for decoupling, but probably could do with a bit more. I've got a trigger input here, which comes from my waveform generator, currently set to 5%. I'm using a frequency of 1 kilohertz. I'm using a high current power supply, and I'm currently just drawing about ½ amp at the moment. Okay, so parameters, I'm just unknown parameter. Well, I won't decipher those numbers, but I'm hopefully going to try and determine the value of the inductance from the indications that I've got. So on the screen at the moment, the top trace is the voltage developed across the source resistor. The source resistor, which is this one here, which is a 0.012 ohm, and so that voltage is the current that's in the through the inductor, and the bottom trace is the pulse waveform. Now values, the top trace is set to 0.5 volt division, so that's about 500 millivolts at the moment. Bottom trace is just fixed at 5. I'm not worried too much for that. The oscilloscope setting is time base is 20 microseconds. So what we're going to do now is observe the I'm going to increase the duty cycle and observe what happens on the current saturation point of the inductor. So if we start to saturate it, we can see that it's actually saturating. It's gone non-linear now, so I'm going to back it off, and I'm going to take a simple measurement to determine the DI by DT, the change of current over a change of time. So I'm going to just increase the sensitivity of the it's just that down there, and we'll shift that down there. So all I'm looking for is a linear change of current versus time. I'm just going to alter the parameters slightly. I'm just going to, because this resistor in the drain of the FET is acting like a bit like negative feedback, so as the current increases, it tends to reduces the bias of the FET. So I'll leave that as it is, and I'm just going to do a duty cycle again, back it off a little bit so we get into a much more linear portion. And what I'll do is I'll be able to do all the workings out for the amount of current through the inductor. So just want to take a snapshot of all the parameters on the screen. So I centralize that point there, I'll use that as my reference. So what we've got there at the moment, we've got the ammeters indicating about ½ amp, but that's only the DC, the average current. I'll need to determine the current of the inductor later on. So let's see what we've got. So we've got on our change of current is from this reference here, so that's my 0 point. That's on 0.1 of 100 millivolts per division, so I've got 100, 200, 270, maybe 260 we'll call that. So we've got 260 there, and we'll take the horizontal resolution. Time base is 5 microseconds per division. And so what we'll do is we'll have a little look. So that's 5, 10, 15, 20, 25, 30, 5, 10, 15, 20, 30, 35, and we'll call that 40. So 40 microseconds at 260 millivolts. So we'll do the DI by DT on that, and I'll try and determine what the inductance was.